Okay. Alrighty. So should I, I'll just say that 3.8 is all with respect to time, and we're going to do all the derivatives implicitly. Okay, so example number 1, let's practice writing these. So you've got letter A. Mortimer is growing at the rate of 3 inches per year. So if you're going to write this, this is a rate, right? This is a rate with respect to time. So if you want to call it like, you could call it anything you want. We call it dm dt. So the rate at which Mortimer is growing is dm dt, and you would express that as 3 inches per year, like that. Okay? And he's not shrinking, he's growing. So it's a positive 3 inches. Okay? That's important to note that. All right, part B. My stock portfolio is losing 5 cents per day. So if you want to call stock S, you could say ds dt for your stock. And since you're losing 5 cents a day, this would be negative 5 cents per day. Okay? Okay. Part C. The radius of a circle gets larger by 4 feet each hour. So dr dt, and it's getting larger, so positive 4 feet per hour. Letter D, the outside temperature is dropping by 5 degrees Fahrenheit per minute. So let's see, I don't know, maybe we'll call temperature big T. So it could be dt, dt, little t. And since it's dropping 5 degrees per minute, it would be negative 5 degrees Fahrenheit per minute. Okay. So you're going to need to be super observant when you're reading these word problems, because they're going to give you that information, and they're not going to come out and say dr dt equals 4. They're going to say it in words, and you're going to need to interpret that into a derivative. Okay. And then we'll make an equation and go from there. All good? Everybody with me so far? Awesome. Great. Okay, cool. Alrighty, so example 2. So let's actually dive in here and do one of these. Starting out with a rectangle. The length of a rectangle is decreasing by 2 inches per second. So let's interpret this. 2 inches per second. So if you want to call L length, then your rate is dl dt, and that is decreasing by 2 inches per second. So this would be negative 2 inches per second. Okay. The width is increasing by 3 inches per second. So increasing, and it's width, 3 inches per second. So if you call W width, then dw dt, and we're increasing, so that's a positive 3 inches per second. Okay. Okay, so when the length is 10 and the width is 6, how fast is the perimeter changing? And then we have to figure out how fast the area is changing. So we've got 2 different things that we need to find the answer to find the rate. So first we go back to perimeter, okay? In order to figure out how fast the perimeter is changing, we need a perimeter formula. So if this is perimeter of a rectangle, what is the formula for perimeter of a rectangle? Right, 2L plus 2W. Okay? All right, so we're trying to figure out, because if you picture it, okay, you've got this rectangle, right? And what's happening is the length is getting shorter, but the width is getting bigger. So it's like if it started out like this, it's turning into, I can't make my fingers probably do it, but if it started out like this, it's turning into like this. Okay, so the rectangle is changing like this. So at some point in time, the length is going to be 10 and the width is going to be 6. So we want to figure out how fast that perimeter is changing when the length and the width are those particular things. Now, here's the catch with this. You do not want to put the 10 and the 6 in now. Don't do that, okay? Because what happens if I put the 10 and the 6 in right now, I get 20 plus 12, which is 32, right? If I take the derivative of that, because you know I'm going to have to find dp dt, right? If I take the derivative of that, what's the derivative of 32 going to be? 0, yeah, and it's not 0 because it's definitely changing at a specific rate, okay? So don't put the given information in until after you take the derivative. Take the derivative first, implicitly, then plug in the given numbers, okay? That's like big thing that you need to remember. Make a little note to yourself to take the derivative first, okay? In fact, I will even write that down because that is very important. So take derivative first, then plug in 10 and 6, okay? All right, so when we take the derivative of this is the review. This will be dp dt. And then when you take the derivative of 2L plus 2W, you have two different variables, and that's fine. You're not, like in the last section, we had to get it all in terms of one variable. You don't have to do that for these. You're going to take it implicitly. So the derivative of 2L is 2 dl dt. Remember, like when we did implicit differentiation before, when you would take the derivative of, like, say it was like 2y, it would be 2 dy dx. You have to do that for these now. So, and then the second one would be plus the derivative of 2w is 2, and then this would be dw dt, like that. Okay? So now you can kind of see, well, I got a dl dt. We were talking about that earlier. That's over here. And I got a dw dt. We were talking about that too. That's right here. So you're going to plug that in and evaluate, okay? Notice when you take the derivative of the perimeter, you don't have a L and a W in your derivative anymore. And that's because perimeter is a linear function. So when you take the derivative of it, the derivative is just going to be a constant times that dl over dt, okay? So that's why there's no like L or just like a plain old L, and there's no like plain old W in this derivative. It's because this was a linear function, like L to the first power, W to the first power. If this was like L squared and this W was like 2W squared, then you'd have a W in your derivative, but it was just to the first power. So that's why it's like this. All right, anyway, plug that in. So this is 2 times dl dt was -2 plus 2 times 3. And then you can simplify that to -4 plus 6, which is 2. So at what rate is the perimeter changing? it's changing at 2, and then since these are application problems, we always put a label on our answer, okay? We were talking about inches per second. Okay, so the perimeter is changing at 2 inches per second. And that's how you do that one, okay? So first step, if you need to, draw a picture. But this was a rectangle, so I hope that we're familiar with what that would look like. We wouldn't need to draw that one. And then second step is take the derivative implicitly. Third step is plug in the given information, okay? And then solve. So now we're going to do the area one. And I have written too big, so I am going to erase this. And we'll do area. Okay. Keep all that given information on the other side there. All right, so now we're going to do area. So area of a rectangle is length times width. So now I want to take the derivative of the area formula. I need to do it implicitly. Now, you've got multiplication there, 2 totally different variables. So this is going to take product rule. So this is your U and this is your V. Okay, don't forget to do that implicitly. So dA dt, remember how to take the derivative of a product. It's going to be U prime V plus V prime U. So the derivative of U is going to be 1 dl dt times V, which is W, plus the derivative of W is going to be 1 dw dt times U, which is L. Okay? Okay. And now you start plugging everything you possibly can that's given to you into that derivative. So dA dt is going to be, well, dl dt is -2. And so this derivative actually has a W and a L in it. So that's where you plug in that information up here, okay? With the length being 10 and the width being 6. So width is W, so that is 6 right there. Plus dW dt is given to us, that was 3. And the length is 10. Any questions about that so far? You guys okay in class? All right, we're all good? Okie doke. All right, now you're just gonna do the arithmetic, right? So this is -12 plus 30, which is 18. So 18. Now, be careful with the label for this because we're talking about area. How is the area changing over time? So when you measure area, that's not just going to be inches, it's going to be inches squared per second. Okay? And that's how it goes. So all these problems are going to be come up with a picture if you need to. Then from there, get the equation. Take the derivative implicitly and then plug in the given information and solve. Okay, so this one was a rectangle. Let's move on to example 3, which is a right triangle. Okay, so right triangle, I'll draw this one because who knows what they're giving us for this. Okay, a right triangle whose sides are changing has sides of 30 and 40 inches at a particular instant. Okay, so if you can picture this like triangle, like who knows what's happening to it, you know? The one side might be getting smaller, the other side might be getting longer. They might both be getting longer, who knows? But we do know at a particular instant that the sides are 30 and 40. Okay. Not the hypotenuse. Otherwise, they would have said hypotenuse. So you can picture like one of the legs is 30 and the other one is 40. Okay. Okay. If the shorter of these two sides is increasing at 3 inches per second and the longer side is decreasing at 5 inches per second, how fast is the area changing and how fast is the hypotenuse changing? All right, so let's start labeling some spots on this rectangle, or not rectangles, triangle, so that it'll like maybe be a little easier to talk about. So I'm going to call this A. I'll call this B. Ooh, lost my triangle. I don't know why that's happening. And this is C. Okay, so have a little right angle there. So let's say, since this is the way I drew it, it looks like A is a little shorter than B. So we'll say A is 30, B is 40, okay? And so since we're talking about it, what would C have to be when A is 30 and B is 40? Yep, good. 50. That's a 3, 4, 5 right triangle, and you can put 10 on, like you can make it 30, 40, 50. You can make it 300, 400, 500. It doesn't matter. It's still a 3, 4, 5 right triangle. So put as many zeros as you want behind them. It'll still just work out to be that every time. So good. All right, now the shorter of the two sides. So the shorter of the two sides is the 30. That is increasing at 3 inches per second. So if this is increasing at 3 inches per second, we can say dA dt, like that. Increasing, so positive, 3 inches per second. Why did I call it dA dt? Because they said it's the shorter one. So of these two, the 30 is the shorter one. So that's why if I called this A, oh my goodness, why is this happening, y'all? All right, anyway, dA dt would be 3 inches per second. All right, and then it says the longer side, so that's going to be B, is decreasing at 5 inches per second. So dB dt is decreasing, that's negative, 5 inches per second. Okay. Okay. Any questions where how I came up with those derivative equations from the word problem? Okay. All right, so let's do A. We want to figure out the area, okay? Or how quickly the area is changing. So, here we go, I got it back. So area of a triangle, for this particular triangle, we know the area is 1/2 base times height. Well, for this particular triangle, our base is B and our height is actually A. So I'm not going to use H. I'm going to use the letters that we actually have. So this will be 1/2 B times A. Okay. Now, we got to take the derivative of this. Okay. Don't put the 30 and the 40 in. Otherwise, when you take the derivative, it'll be 0. We don't want that to happen. So dA dt. This is product rule again. So what I'm going to do is I'm going to put the 1/2. I guess I'm not. Holy cow. I was going to put the 1/2 with the A. Or no, I was going to put it, what was first? I put the B first, didn't I? Okay, so I was going to put that with the B. So that's your U. And then times A. This is your V. okay? Some of you may just want to pull the 1/2 out and deal with it later. I'm just going to put it in there now so that it's done. We're going to do product rule now, okay? So u prime v plus v prime u. So the derivative of 1/2 b will be 1/2 dB dt times a, right? Because you have to do u prime times v, so 1/2 dB dt times a, plus the derivative of a is 1 dA dt times the first thing, which was 1/2 b. All right. Now, after you get through taking the derivative, you plug in all the given information. So we've got all kinds of given information. We've got 3 inches per second. We got -5 over here, inches per second. You've got a 30, you got a 40. Plug everything in there that you need. So this will be 1/2 times dB dt, which is -5, times a, which is 30, plus dA dt, which is 3, times 1/2, times b, which is 40. And take a look at that and make sure you're okay with where I got all those numbers from. Okay. Okay, now simplify this however you want to, the fastest way you possibly can. I don't have Desmos or my calculator right next to me, so I'm just going to try to simplify things as fast as I can. So I know 2 goes into 30, oh goodness, 15 times. That was a 15, and this was a -5. So -5 times 15 is -75. I know 2 goes into 40 20 times, so this would be, why am I losing all of my stuff, you guys? -75 plus 60, I get -15. Double check. Okay, cool. So it ends up being -15. This is area, and we were measuring in inches. So this is -15 inches squared because it's area per second, like that. Okay. Okay. So that was that part. Now we need to do the hypotenuse. So I'm going to erase some of this. We still need the derivatives that we had up there, the dA dt and dB dt. And let's see here. I definitely don't want that. Let's make it just like a tiny bit thicker. All right. So now we're trying to figure out how fast the hypotenuse is changing. All right, so now we're talking about the hypotenuse of a right triangle. The only thing that we really know that talks about a hypotenuse, besides some trigonometry, which we are not going to do trig for this because you only do trig when they talk about an angle. They're not talking about an angle in this problem at all. So no trig. The only other choice, Pythagorean theorem. Okay. So if we want to know how fast the hypotenuse is changing, that means that we're looking for dC dt. dC dt would be how fast the hypotenuse is changing. All right, so take the derivative of the Pythagorean theorem, implicitly plug in everything that you're given, okay? So this will be 2a dA dt plus 2b, right? Bring the 2 out in the front. B dB dt equals, take the derivative of the other side of the equation too, 2c dc dt. Okay, there you go. That's what we're looking for, dc dt. Everything else we have information for. So like we can plug in all the numbers for everything else, including C. We figured out C at the very beginning. Okay. So you're going to do, let's see, 2 times, I don't know where I'm going to squeeze this. I guess I'm going to erase this over here. What'd you say? Oh yeah, I could write down here, I suppose. Yeah, I can do that. Okay, so this would be 2 times A was 30, right? dA dt is 3 plus 2 times 40, right? B was 40. dB dt was negative 5 equals 2 times C. We figured out what C is. That was 50. And then dC dt is what we're looking for. Okay? All right. So 2 times 3 is 6. 6 times 30 is 180. That's 180 plus. 2 times 40 is 80, or 2 times negative 5 is negative 10. That might be easier. 2 times negative 5 is negative 10. Negative 10 times 40 is negative, right? 400 equals 2 times 50 is 100 times dC dt. Okay. Get the dC dt by itself. So 180 minus 400. Negative 220, thanks. Equals 100 dC dt. Divide by 100 is the same as moving the decimal point over 2 spots. So negative 2.20 equals dC dt. Okay? So that negative 2.20 represents how fast the hypotenuse is changing. So is the hypotenuse getting longer or is it getting shorter? Yeah, it's getting shorter because this is negative. And so this would be negative 2.20. And we were in inches. So this is inches, plain old inches, because a hypotenuse is a linear length. So inches per second. So if like on an exam or I asked you a question on the homework about this, you could say the hypotenuse is decreasing in length or shrinking or however you want to put it at a rate of 2.2 inches per second at that moment in time. Okay, at that particular instant in time. Take a look at that and see if there's anything you want to ask me about. What if you did what? Say it again. Uh-huh. Oh, yeah. You could solve for C. Now, that would be a little bit of a pain in the neck because you'd have a square root over top of the a squared plus b squared, which would require you to do chain rule in addition to implicit, but absolutely it'll still work. Yeah, absolutely. Yep. The question was like, if this would have worked out, if we would have solved for C at the very beginning, like right here, if we would have solved this for C by taking a square root of both sides and then doing dC dt, if it would have, you got the same answer. Yeah, you totally get the same answer. It's just that you'd have, like, it would look like this. And so there's your dC dt, but this would require you to do chain rule You'd have to bring a 1/2 out in front and all that good stuff, but it would end up to be the same thing. Yep, absolutely. Okay, so the next page of the notes is just lots of little pointers for you. Lots and lots of stuff. Like if you like steps, here you go. There's like all kinds, everything all like spelled out a lot. Okay, so I will let you just go ahead and enjoy that on your own time. I'm going to move on to the next example. Okay, because we're basically doing all those steps that are outlined on that last page. We're just kind of doing them actively right now. Okay, so example 4. Now it's getting kind of fun here. So we have an oil tank spills oil that spreads in a circular pattern whose radius r increases at the rate of 50 feet per minute. So you got an oil spill. As the oil's dripping, or I don't know, hopefully not like gushing out. Maybe that's the case. Who knows? 50 feet per minute. So the oil's coming out and it's like spreading out in a circular pattern. Okay. Like in the water, right? Okay. So here's your circle. R, right, is your radius. It says the radius is increasing at a rate of 50 feet per minute. So right away, you're like, ah, okay, I recognize that. That is dr dt. And it's increasing. So this is 50 feet per minute. Okay? All right. So how fast are both the circumference and the area of the spill increasing when the radius of the spill is exactly 20 feet? Okay, so we need to figure out the rate that the circumference is changing, and then we also need to figure out the rate of the area. So two different things. So we'll do circumference first. Circumference equals, formula for circumference is 2 pi r. Okay, remember 2 and pi are constants. Don't treat this as product rule. This is just a constant 2 pi times the radius. So if I want to see how fast that circumference is changing, I'm really looking for dc dt. That's the rate that the circumference is changing. So we take the derivative implicitly. So if you have a constant in front of a variable, the derivative is just that constant times the derivative of the variable, which would be dr dt. Okay, so dc dt is going to equal 2 times pi times that dr dt that we were given, which is 50. Okay, and your most exact answer is going to be in terms of pi, so let's just go with that. So 50 times 2 is 100, so this would be 100 pi, and this is describing circumference, which is around the outside, so that's a linear measurement. So this is going to be 100 pi feet per minute. Okay, so the radius is changing at 50 feet per minute. The circumference is changing at 100 pi feet. So 100 pi is like 314 feet per minute, you guys, if you want to like think about that, right? So 3 feet in a yard, right? So 300 feet would be like 100 yards. That's like a football field, you guys. Take the length of a football field and a little bit more for this example and wrap it around and make a circle. That's how big that oil spill is. Okay. and that's just, change, and that's changing. Okay, that's how fast it's changing per minute. Okay, all right, so let's look at the other part. So the other part is asking you for how quickly the area is changing. So the area is the area of a circle, and we know that that is pi r squared. So when you take the derivative of that, that'll be dA dt equals, take the derivative of pi r squared, right? So that'll be, bring the 2 out in front, 2 pi r dr dt. Don't forget to do it implicitly, because this is with respect to time. Okay. Okay, so now we plug everything in we know. So dA dt equals 2 times pi times the radius. Well, that's where we use this now. That's our opportunity to plug that 20 in, times the 50 that we had before. So 2 times pi times 20 times 50 is going to be, let's see, what will that be? 50 times 20. 50 times 20 is like 1,000. So this will be 1,000 times 2, 2,000 pi. And this is area now, how area is changing. So this will be feet squared per minute. Okay? 2,000 pi feet squared per minute. All right. Any questions so far? You guys okay at home? Awesome. Okay, cool. All right, so now we're going to make it even more fun. I'm going to have to erase some stuff, but that's okay. It says if the depth of the oil spill, okay, so like first it starts off on the surface of the water, and then it starts to like ooze down into the water, right? If that depth, how deep it is in the water, is represented as 2r squared plus 1, how fast is the volume of the oil spill changing at this moment? Okay. Well, let me erase some stuff so that we can kind of like see what this is talking about. All right, so you've got, so here's the water, right? So you've got this oil spill. We'll go black, inky black, right? So it's got like kind of like a circle on the surface of the water, right? And so as time goes on, it's like sinking. Okay, so it kind of has like, well, the depth is 2r squared plus 1, which is a parabola. Like an r squared, that's like a quadratic equation. So like kind of like this kind of thing. I don't know why I'm losing my part of my drawing. But like your depth, it's like sinking down into the water. Okay? So it's some kind of 3D solid when it sinks. The main thing that you need to think of is that volume is area of the base times height. Like if you find the volume of any three-dimensional object, it's always the area of the base times the height. Okay, now we know specific things about cones and cylinders, that they have relationships where a cone is a third of a cylinder. We don't have that fancy shape for this. This is not known to be a cone or anything. It's just a 3D shape. So the area of the base, well, we know that the base of this oil spill is in the shape of a circle. So that's going to be pi r squared. right? Area of a circle is pi r squared. The height of this 3D object is that 2r squared plus 1. This represents depth. Okay? Oh my goodness. All right. So that's going to go in for your h. So this will be 2r squared plus 1. Do you follow me so far on that? Okay, cool. Awesome. So what are we looking for? We're looking for how fast is the volume still changing? How fast is the volume changing? So we're looking for dV dt. Now, over here, conveniently, we are all in terms of the same variable. He was really nice in this example and gave us a height that was in terms of r. So we could make this like a little bit easier to look at. So this could be, let's see, if I do like the distributive property here, like this, oh my gosh, you guys, I'm sure like somebody must know why this is happening to me. 2r, no, that wasn't the squared part, was it? Sorry, you guys. What was it originally? Pi r squared is like pi r squared times 2r squared plus 1. Okay. Okay, so if I do the distributive property, this would turn out to 2 pi r to the 4th, right? Like if I do that without trying to touch it anymore. And then plus pi r squared times 1 would just be pi r squared. Like I just did the distributive property with that pi r squared. So now when you take the derivative of this, now you still, even though it's all in terms of one variable, you're still doing it implicitly, okay? Because it's still with respect to time. So when you take the derivative of 2 pi r to the 4th, bring the 4 out in front, this will become 8 pi r to the 3rd power dr dt. Plus, take the derivative of the second part, so this will be 2 pi r times dr dt. Now you're going to plug in everything that you know. We know dr dt is this 50. I know that r is 20 right here. So we're going to plug all that in and get an answer. Might need your help. Probably will need your help because I don't think I can do these ones. So 8 times pi times like 20 cubed times 50 plus 2 times pi times 20 times 50. Yeah, somebody go ahead and just figure that out for me. What's happening to my picture here? I'm like losing this lady's head. Was there even a head there to begin with? Anybody have 8 times pi times 20 cubed times 50? You can tell it to me in terms of pi. I don't need to have the 3.14 in there. 6 billion? Oh, 64. Okay. Okay. 6, oops. 6, 4, how many zeros? 8? 1, 2, 3, 7, 8. And then a pi? Should just be a regular pi. Oh, okay, so you multiplied all that? Okay. So 20 cubed I know is 8,000. This would be 64,000. Yeah, you guys. Anybody have that? 3,202,000. 100? Okay. Like this? And then a pi? Okay. All right. Can anybody confirm that? Y'all getting that at home? This is, what would be the label? Feet. Cubed, because it's volume, so cubic feet. Okay, cool. Thanks, guys. Per minute. So since this is the change in volume, make sure you have cubic. Oh goodness, I lost it. Make sure I have. There we are, back at it. So make sure that you have cubic feet per minute. Okay. Okay. All right, example 5. A 10-foot ladder is leaning against a vertical wall. The lower end of the ladder is being pulled away from the wall at a rate of 2 feet per second. When the lower end of the ladder is 6 feet away from the wall, A, how fast is the ladder sliding down the wall? All right, so let's draw a picture. So I know we have a picture over here. Well, I guess I could just use this lovely picture with this like headless person. Let's see. So 10-foot ladder. Ooh, so that's 10. And then this, the bottom part of the ladder is being pulled away from the wall. So I got to draw my own picture. This is 10. Bottom of the ladder is being pulled away. So if the bottom of the ladder is being pulled away from the wall, this distance right here, like if I call this A, this distance is increasing from the wall. Okay, so that means dA dt is going to be positive, and it's at a rate of 2 feet per second. So this will be 2 feet per second. If you were pushing the ladder up against the wall, that distance would be decreasing and your dA dt would be negative. But we're not doing that. We're pulling the ladder away from the wall, so the bottom distance is increasing. So it's a positive 2. All right. And that's all they tell us, right? They say when the lower end is 6, so when this A is 6, how fast is the ladder sliding down the wall? So here's the wall, right? So if the ladder is sliding down the wall, we're going to call this, we'll call that side of the wall B. We're looking for dB dt. How fast? That's a rate. How fast is the ladder sliding down the wall? So you're looking for dB dt. You know that A is 6. And we know that the ladder is 10 feet long. So when A is 6 and the ladder is 10, which is the hypotenuse, what will B equal? Yeah, 8. Right? Because that would be a 6, 8, 10 right triangle. All right. So we need to come up with an equation that relates those 3 sides of that right triangle. The only thing we've got to work with is Pythagorean theorem. You're not going to do trigonometry with this because they don't talk about any angles. Remember, the only time you use trig is when they talk about an angle. So we're going to do Pythagorean theorem. A squared plus B squared equals C squared. Take the derivative implicitly. So 2a dA dt plus 2b dB dt equals 2c dC dt. I'm like running into that guy's legs. Okay. Plug in everything that you know. So I know A is 6, so 2 times 6. I know dA dt is 2, so times 2, plus 2 times B, which is 8. We figured that out. dB dt, don't know what that is. That's what I'm looking for, so we'll leave that. Equals 2 times C, well, C is our hypotenuse, so that's 10, times dC dt. Okay, so what just happened here? We've got 2 unknowns. I'm trying to solve for dB dt, but I've got dC dt right there. What do I put in for dC dt? Yeah, that's the rate that the ladder is changing. And is the ladder changing? It's changing position, but it's still it's still a 10-foot ladder. No matter where you put it up against the wall, it's still a 10-foot ladder. So the length of the ladder is not changing, right? So therefore, dC dt, you were right, Justin, is 0. So that means this whole side over here is 2 times 10 times 0, which is going to be 0. Length of the ladder is not changing. So therefore, that comes out to be 0. Okay. All right. So 2 times 6 is 12. 12 times 2 is 24. That's 24. Plus 2 times 8 is 16 dB dt equals 0. Solve for dB dt. So we'll do a little subtraction, divide. Yeah, good. Y'all get -3/2. And so how would we label that? Well, it's how fast the ladder is moving down the wall. So this is going to be in feet per second. Oh, I had a whole ton more space and I didn't even realize it. Well, I guess I'll need it for the other parts. So -3/2. All right. Any questions about that? So we used Pythagorean theorem and we took the derivative. Okay, part B. How fast is the angle between the ground and the ladder changing? So as we pull this ladder away from the wall, what's happening here? Like it starts maybe like this, And then that angle's gonna get smaller and smaller and smaller until finally that ladder's like laying on the ground and the angle's 0. And you don't even have a triangle anymore. So the angle is changing. How fast is that angle changing? Well, let me erase some stuff here. So, well, actually, I guess I have some more space, right? So I'm gonna make the triangle, okay? I'm gonna put the angle right there because they said the angle with the ground. Here's my ladder. I know that's 10 and that's not changing. And what else here? We're still talking about 6 feet away from the ground, from the wall. So when A is 6 and DA, DT is still 2. That hasn't changed. Okay. Okay. I know what it is. I'm writing on a PDF. I need to open this up in a different thing next time so that I can draw on it better. Okay, so did you guys have a question or no? No. Okay. All righty. So you got an angle. Ah, we have an angle. So therefore, trigonometry. Yay. All right. So at this point, you could use any trig formula because we figured out that this other side right here is 8. So really, you could use any trig formula that you want. They'll all work. I would not use this just because there may be some chance, like let's say you're taking a test and you have this problem on a test. Let's say for some silly reason, you calculate this wrong and like you come up with 7.5 or something for this side instead of 8. If you then use that side, that 7.5 that's not right in the rest of your work, the rest of your answers are going to be wrong. So the AP reader, they're very nice about this, surprisingly. They won't take the points off if you do the rest of your work correctly with the wrong number. But just to be safe, I'm not going to use that. Okay, I know we're right, but I'm going to stick with just the given information because I know that that's true. So if I have a 6 and I have a 10 to work with, what trig function would use this side on the ground and the hypotenuse?
Cosine.
Yep, cosine. So it is cosine of the angle equals the adjacent side over the hypotenuse. Okay. All right. So actually, I did not write that very nicely. I should have made a little a because that's what I labeled my triangle with, a little a. Okay. Now, let's think about this. The angle, we know the angle's changing, right? The angle's changing as we pull the ladder away. This distance, A, right here, this distance, that's changing too, because we're pulling the ladder away from the wall. So this distance is also changing down here along the bottom. That distance is changing. At a particular moment in time, it's 6, but really it's being pulled away from the wall. So that distance is changing. So A is changing. Is H changing? What's H represent? The hypotenuse, which is the ladder. H is not changing, okay? The hypotenuse is staying put. So you can, at this point, put the 10 in here because it's not changing. It's staying 10 the entire time. The length of the ladder is not going anywhere. It's just staying 10. Everything else, though, has to stay as a variable and take the derivative implicitly. So what is the derivative of cosine of theta? Negative sine theta. And then we're going to do this implicitly because we talked about how that angle is also changing. So this is times d theta dt. We need that d theta dt in our equation because that's what we're looking for. They're asking us how fast is the angle changing. So I need that d theta dt in there. Now, equals a over 10. So this 10 is just a constant. You don't have to do quotient rule with this. Think of this as like just 1/10 times a, like that. So if you take the derivative of this, it's just going to be 1/10 times the derivative of a, which is dA dt. Okay, now you're going to plug in everything you know. All right, so you've got, let's work right to left, just for fun. So I know dA dt is 2 times 1/10. I'm looking for d theta dt, so that's going to stay unknown. How am I going to do the sine of theta? It'll be negative because there's a negative sign right there. Yeah, so sine theta is opposite over hypotenuse. So at this point, we're forced to use that opposite side. Okay, so if this is 6 and this is 10, this opposite side we figured out is 8. So the sine is going to be 8 over 10. See, we didn't need to know what that angle was. We can just use the sides of a triangle. You know that sine is opposite over hypotenuse. So the sine of theta for this triangle is going to be 8 over 10. And it's negative because there was a negative in front of our sine theta. All right, now all you have to do is maneuver those fractions to get the d theta dt by itself. So d theta dt equals, let's see, this would be 2/10. And then to get this negative 8/10 over to the other side, I'm going to multiply by its reciprocal. So negative 10 over 8. And then these 10s will cancel, which is kind of nice. So this will be negative 2 over 8, which is negative 1/4. Now, the label on this one, we're talking about how fast the angle is changing. And this is something I want you to remember. Whenever we talk about angles, we are in radians, okay? Not degrees. So this will be in negative 1/4 radians per, what were we talking, seconds or minutes? Seconds. So negative 1/4 radians per second. And so you're looking at it wondering if it's reasonable, right? Well, one way that we can tell that this is reasonable is that our rate is negative. And that's a good thing because if our rate is negative, that means that the angle is getting smaller. It's decreasing. So that's a good sign. Okay. Okay. We got a couple more little parts to this. How fast is the area of the triangle formed by the ladder and the two walls changing? All right, so area of the triangle formed by the ladder and the two walls. How fast is the area changing? Okay, so let's see, where can I squeeze this? I guess I'll try to put it over here. Is this letter C? Yes. So if you have this triangle again, and this is 6, this is 8, your area is 1/2 base times height, which in this case, the base is A and the height is B. If you want to know how fast that is changing, you take the derivative of that implicitly. So this is product rule. This is U and this is V. Okay. So derivative of U is going to be 1/2 dA dt times B plus the derivative of B is dB dt times 1/2 A, or I'm just going to squeeze it in here as A over 2. All right, so now you're going to plug in everything that you know. So we know that dA dt was 2, right? Remember that was the rate at which the distance was increasing. The ladder was being pulled away from the wall. I know B is 8. We know dB dt because we found that out way back in like the first part. So you can put that in there, -3/2. And then times A over 2, so 6 over 2. Okay, simplify. The 2's cancel, you get an 8. And then, goodness, what happens here? -18 over 4, something like that. So minus 18 over 4. So this would be 32 over 4 minus 18 over 4. 6? No. 14 over 4? 14 over 4, I think, which is 7/2. Okay. Now, that's area. So that is going to be in feet. Yeah, feet squared per second. All right. So that's a positive answer. So it must be our area is getting larger at that moment in time. All right. Questions on any of that so far? That was a lot of stuff to talk about. We still have part B. Okay. So, part D. What is the acceleration of the ladder down the wall? Acceleration. Well, if the rate at which the ladder is going down the wall was this, we found that right there. dB dt is -3/2 feet per second. If that is what the velocity or the rate at which the ladder is going down the wall. If you took the derivative of that, what would you get for the acceleration? Yeah, that would be 0. So your acceleration is actually 0. It's going down at a constant rate. So therefore, it's not accelerating. There is no it's not like as it goes down, it gets faster and faster and faster, like an object falling from the sky. This is being pulled away at a constant rate, so therefore it's going down at a constant rate. So part D is 0. Okay. If it were falling on its own, but this is being pulled away, so it's a controlled movement. So therefore you don't have to take gravity into account. Okay. You're holding the ladder and steadily, like you're steadily moving it away at 2 feet per second. So it's not increasing in speed. It's constant. Okay. The bell's going to ring here in like 2 minutes. And that was a lot of stuff to talk about today. We will pick up with the rest of these tomorrow. And in the meantime, try some of the problems and